So let me go up one notch. Okay. All right. Answer one question from last time. Well, actually, it came in more than once. Al sometimes steers around the camera. You know, this camera up there. It secretly steers it around during class. So some people are wondering, like, magic was happening. I wasn't even aware the camera was zooming in. But Al, who runs lecture demo, secret. So anyway, I appreciate it. All right. What problem set? This was problem set 4. Is just due now. Is it? It's 4. Yeah. Problem set 5. It's due on Wednesday. I realize that compresses the time scale, but Wednesday is sort of my traditional day for having them due, and I postponed this one to Friday just to accommodate the break. But now we're back on normal schedule. So with balloons, story of balloons, and I'll get, I hope, a little bit into the story of water distribution today. I realize I had not put up a lecture video for that yet, but I'll work on that. With balloons, I showed you last time things like air and other fluids push on things by way of pressure, which ultimately produces forces, but in order to figure out the force involved exerted by the air pressure here on that wall, you have to take the air pressure, which is how hard it pushes on every square meter it encounters, and multiply that by how many square meters the wall is, and you get the total force that air's pressure exerts on that wall. You can do those kinds of calculations. It's not really a big part of this class. Obviously, there are situations in which people do care about those sorts of things. I showed you things like the air pressure is significant. It can do things like hold together a split jar, a split sphere, so it's very hard to separate the two halves. We put a balloon inside the bell jar and showed you what happens if the balloon stops having air pressure around it, pushing inward on it. The balloon swelled larger and larger. I should say 2 cents now that I've talked more. Subsequently, I talked more in the class. I can now explain why the balloon got larger. The balloon is trying to find an equilibrium, a situation in which there's zero net force on all the pieces. And as I remove the air from around the balloon, the air inside the balloon still had full pressure. It pushes out way too hard on the skin of the balloon, given that there's not much push in on the outside of the skin of the balloon. So the balloon expanded, and that reduced the density of the gas inside the balloon. Less mass per volume, that's density. So we're spreading out the little air molecules, so they're not as packed as they were before. They therefore don't push as hard on surfaces because there are fewer of them in every cubic centimeter, and therefore they don't hit as often on the walls. So the push goes down. So you reach a new equilibrium. Every time I remove some air in the bell jar, I'm leading up to something here, so bear with me. Every time we reduce the pressure in the bell jar, the balloon swells a little more. Each time it's doing that, it's finding a new equilibrium where it's reduced the density of the gas inside it enough that the push in, push out, they pretty much balance and so on, until finally the balloon burst. This, incidentally, is the fate of all helium balloons when you let them go. They go up higher and higher, and they swell in the same way. I told you that the atmospheric pressure is highest down here, less up there. So carrying a balloon to great height is a lot like putting it in a bell jar and pumping the air out from outside. So the poor helium balloon keeps getting bigger and bigger, trying always to find a new equilibrium until finally the balloon can't tolerate it, and it bursts somewhere way up there. I guess the only exceptions are some of the balloons that they send way up into the highest reaches of the atmosphere, the government test balloons that they set up. And those are special balloons that can expand unbelievably. They're just huge bags that they start very small down here on the ground, and they swell to hundreds of times their size by the time they're way up high. That's a whole other story. Well, I said I'm leading up to something. What I'm leading up to is I got some fresh marshmallows. So, some demonstrations are too important to leave behind completely. So there are 2 good ways to puff a marshmallow. The one you're familiar with is you hold it over a fire and you heat up the gas inside. And I told you last time that as the temperature of a gas increases, if you keep the density the same, so the same number of particles in every cubic centimeter, if you heat them up, they're moving faster, they hit more often to any surface, and they hit harder. So the pressure goes up. The long and short of it is the pressure goes up when you heat up a gas, everything else kept the same. And so in this case, again, the bubbles have to swell to find a new equilibrium. The pressure is too high inside them when they're hot. So they get bigger to balance the pressure inside, pressure outside. And as they get hotter, they get bigger and bigger. So that's what you're doing when you're puffing marshmallows. That's one way to do it. The physicist's way to puff marshmallows, which you can do without high temperatures, is to take the air out from around them. Alternatively, I suppose you could shoot marshmallows up in a rocket to great altitude, and it would do the same thing. Yeah, the hard way to puff marshmallows. All right. Okay, there's Marshmallow Man. We can zoom in on Marshmallow Man. It's preset 1. Oh. Ooh. There he is. Ooh. We have this usual problem of, can you see it? Can you not see it? I don't know. It's a pain in the neck. Need better lighting. So we'll put Marshmallow Men into the bell jar and pump out all the air. Ready? All right, it is actually pumping. So this is a machine that is, you can't attract the air through these pipes. But what you can do is you can make a place where the air will flow by virtue of its own pressure. It pushes itself into this device, which doesn't let it back. It's just being sort of, it's not attracted into the pump. It's simply allowed to flow into the pump and then not allowed to flow back. Anyway, looking back at Marshmallow Man, you see Marshmallow Man's getting bigger. Each marshmallow is swelling. The marshmallows finally are just, they're air whipped into some sort of sugar syrupy stuff. And every bubble inside there is getting larger as the pressure outside decreases and the bubble has to swell so that its density decreases and therefore its pressure decreases. Then we get a new equilibrium. And Marshmallow Man's getting close to full size. Just for comparison, there's the original Marshmallow. Is that really compelling? Not as compelling as I'd like. Well, you'll see the more important effect when I let the air back in. This works best with the freshest possible marshmallows. Maybe I'll take them back, but I'll show you what they'll look like before I take them back. Okay, let's call that done, and I'm going to let the air back in. So I'll go back to Harris Teeter and say, look at these marshmallows. What's wrong with them? I mean, the other patter or shtick to deal with it is like Marshmallow Dan was on steroids for a while there, and then now you took him off steroids. Look what happened. All right, and yes, you can still eat them. They still taste the same, but they're kind of icky. Any questions about why that happens? Yeah.
Is that the same thing that happens with apples? Like, you know how
Is it the same thing that happens to apples, that they shrivel up? If they lose as they dry up, as the water comes out, the water was pushing out, keep giving it its size, and the atmospheric pressure is pushing in. As the water disappears and there's just nothing there to replace it, it just gets pushed in. Yeah, so things collapse. I said last time that in general, sort of apropos of that question, is in general we don't even notice atmospheric pressure. It's just around. You have to sort of move to even notice the air is there. But it is really pushing in on us a lot. This has no effect on the parts of us that are solids and liquids. Solids and liquids are nearly incompressible, meaning that no matter how hard you push on them, it's very difficult to notice any change in volume. Do they get smaller if you push harder? who knows? If you step on a penny being an incompressible piece of, well, it's not even copper anymore. Pick a coin. Step on it, it barely gets any smaller because it's an incompressible material. You can push very hard, and you can think of this in terms of pressure. It barely changes in volume. Same with water. You can take a container of a liter bottle of water, squeeze as hard as you like, it's going to still be a liter. You know, it'll be slightly less, but just so little you never notice. Gases you can squeeze. You can make them, you can pack them tighter. And so the presence of gas in us is an issue. If we suddenly were to be exposed to high pressure, much higher pressure than the atmospheric pressure, most of our bodies would be unaffected, but our lungs would get smaller because they are filled with air. So if you go diving, and particularly some of these people who go way deep in the water doing breath hold diving, they'll hold their breath and then try to go down well into the water, tens, hundreds of feet. Their lungs shrink in volume a lot because the gas inside has to be packed more tightly to push outward enough to tolerate, to reach equilibrium relative to this rapidly increasing pressure of water around them. I don't know whether I told you that, I didn't say it yet, or the idea that the Earth's atmosphere has this gradient in pressure, so that you come down from way up high, the pressure is increasing, but you have to go pretty far before it increases significantly. That's not so true if you go into water. Water is much denser than air. So as you go deeper into water, the weight overhead increases rapidly, much more rapidly than air. So if you go down just 10 meters in water, about the height of this room, maybe a little more, that added weight overhead means that the local pressure has to increase by a lot, by about 1 atmosphere, which is to say that if you go in a swimming pool and you go down about that far, that overhead you have the weight of the atmosphere, which results in the local pressure being 1 atmosphere, atmospheric pressure, 1 atmosphere, and you go 10 meters further into water, you're up to 2 atmospheres of total pressure. That means the weight of the air overhead all the way to the top of the atmosphere is about the same as the weight of 10 meters of water overhead. It's heavier stuff, much more dense stuff. Is that okay? So the pressure is rising rapidly as you go down, and this is why, if you do go diving, you feel your lungs get smaller. Yeah, Amelia? So Amelia's wondering why the marshmallows don't look the same as they did before. Which is a great question I should have said, is the balloons got bigger and bigger. It's the balloons. The bubbles in the marshmallows got bigger and bigger up to a point. They were all bursting. And what I was disappointed with when I observed that the marshmallows got bigger but not very much bigger is because they start to leak early. You can't hear them pop, but they're all popping. And once they pop, they sort of reseal. They kind of they blow a little bubble, and then they reseal. And so we've lost gas molecules. During the inflating time, when I was taking air out of the bell jar, the bubbles were popping, losing their molecules to the pump, and then resealing. So now they're bubbles with not enough gas inside. And when I let the air back in, the atmospheric pressure crushed those bubbles to very small size. Is that okay? Yeah. Other questions? There are probably 1,000 applications of this sort of play with the pressure and make things bigger and smaller, and then cooking is going to be filled with them. But let's go on to other things. So those marshmallows really have changed. They have fewer gas molecules inside than they had before. They therefore occupy much less volume. They're composed of partly of a syrupy liquid and partly of gas, and we've pretty much stolen all the gas. And so they're not occupying much space anymore. Okay? So at this point, I went to the hot air balloon, which I'll do again, but I'll lead into it more carefully. Gases create pressure, exert pressure by virtue of the density of the gas. We'll pick a specific gas, air. But by virtue of the density of the air and the temperature of the air. They're both important. And it's approximately true that the pressure of air is proportional to its density times its temperature. So if you double the density, which is to say you pack twice as much air into the same volume, you double the pressure. It's a very good approximation. And so when you're pumping air into the tires of your bicycle or your car, you're packing in the air molecules. The pressure I told you for atmosphere is 100,000, give or take, 100,000 newtons per square meter. In the United States, that's a relatively less familiar unit of pressure. The one that's most common that you may well have heard is pounds per square inch, or PSI. It's going to be there for the rest of our lives, certainly my life and probably your life. These things are so entrenched, they're very hard to dislodge. So atmospheric pressure is just short of 15 pounds per square inch. Another thing you might remember. And that means when you inflate your tires, and the tires on a bicycle, they'll typically want pretty good pressure, 50 psi, 50 pounds per square inch. That's in excess of atmospheric pressure. So that means the real pressure inside a bicycle tire is about 50 pounds plus 15. It's about 60 and change pounds per square inch. That's about 4 times atmospheric pressure. Is that okay? So it's about 4 times atmospheric density in there. So if you want to look inside the tire, the air molecules are packed 4 times as tightly as before. They're 4 times as many in every cubic centimeter. Is that okay? Car tires, not so much pressure. They're typically, they want about 32 pounds per square inch. So that's on top of ordinary atmospheric pressure. So that's about 3 times as dense as ambient pressure. Incidentally, public service announcement, why do you care what the pressure inside your tire is? Because when the tire rolls, I told you about 2 types of friction. Static friction, sliding friction. Sliding friction wastes energy. Well, when a tire rolls, even though it's doing the touch and release story that I've talked about, and therefore is in principle doing static friction only, actually, as the tire lands, it flattens out a bit because it's got to press against the ground. It's using air pressure inside it to support the car to some extent, and it doesn't touch it at like one point on the ground. It spreads a bit, and the less pressure you have inside the tire, the more it has to spread before it reaches equilibrium. So underinflated tires spread out a lot, and you see this. You can see tires that are underinflated are they're short. The bottom part of the tire looks kind of short on the ground, and it's got a big contact surface. And that contact surface, in the act of spreading out as it lands and coming back to curved as it lifts off, scuffs across the surface and wastes energy. So the less inflated your tire is, whether it's a bicycle tire or a car tire, the more of another sort of friction you get, sometimes called rolling friction, you get in a car tire. And that involves not only wasting energy, but wearing your tire. So this is why they nudge you to keep your tires of your car or bicycle properly inflated. It's actually saving you gasoline, and it's saving wear and tear on your tires. Is that okay? You're basically, the physics of how a tire works is actually pretty complicated, more so than I thought before I looked into it many years ago. But you can imagine, for this, how does this balloon support itself when it sits on the table? Because it has a weight, setting aside the buoyant force and stuff. It's got a weight. It's sitting here. It actually has to flatten out on the surface so that that bottom layer is being pushed down by air pressure. It's hard, but it's too hard to do on the fly here. But you can imagine as I shove down on this thing, add weight, it flattens out more and more. It's pushing on more and more surface. And it's using air pressure is part of the force it exerts down, which is getting a force up to compensate. I will leave it. I can get lost in that one. What I wanted to continue with then is we play with density and you get pressure changes. More density, more pressure, more, and so on. What about temperature? Because this is leading into hot air balloons. To a very good approximation, if you double the temperature of the gas, you also double its pressure. Why so? And there is I'm going to come back to temperature in a minute. Why is that so? It's because as you heat up the gas, the average thermal kinetic energy of each particle, it's a lot of words, but basically average, like don't follow just one particle, look at all of them and average. Thermal, look at the kinetic energy associated with the molecules jiggling around, not with the whole balloon flying across the room. So it's the thermal part of their motion. Kinetic energy, that's the only part you pay attention to. So forget potential energies. The average thermal kinetic energy of the particles in the gas is proportional to temperature. Double the temperature, you double the average thermal kinetic energy of the particles. If that's too many words, don't worry about it. It's just basically as you heat the stuff up, things are moving faster. And they hit harder and they hit more often. And so the pressure goes up. All right? So far, that's okay, I hope. Now about temperature. Our temperature scales, the ones that we're most familiar with, which are probably Fahrenheit in the United States, Celsius everywhere else. For those of you who don't know offhand what Celsius is like, the Fahrenheit scale puts the freezing melting temperature of water and ice at 32 degrees. So when it's 32 degrees out, you can expect water and ice to be interesting, coexisting in fact, which we'll come to, but we're not for a little while. So at 32 Fahrenheit, that's freezing, right? That's 0 Celsius. So Celsius scale puts those two, puts the melting freezing transition right at 0. Fahrenheit puts it at 32. The spacing of Celsius, the Celsius degrees are bigger than the Fahrenheit degrees by a factor of 9/5. But everything else, they're both useful scales. You may be able to think in both. Doesn't matter. But the temperature scale that I'm talking about here, that we need when I say if you double the temperature, you double the pressure of the gas, keeping everything else the same. We need a temperature scale that starts with a real 0. These scales, Fahrenheit and Celsius, 0 is nothing special, nothing really special. The 0 of the Fahrenheit scale is colder than the freezing transition of water and ice, but it's sort of an arbitrary 0. What special thing happens at 0 Fahrenheit? And it turns out it's an ancient thing that had to do with a mixture of salt and ice that gives that temperature. But it's nothing special, and you can go below 0, no problem. It happens once in a blue moon here in Charlottesville. The 0 of Celsius is kind of interesting. It's the freezing melting temperature for water and ice, but you can go below 0 there too. We need a temperature scale where you can't go below 0, where 0 is really when you've run out of all thermal kinetic energy. So that the average thermal kinetic energy of the particles in a gas at this 0, it's 0 average thermal kinetic energy. There is none available to be had. So it's called absolute 0. That 0 is absolute 0. And a temperature scale that's built with its 0 corresponding to absolute 0, when there's no thermal kinetic energy to be had, is just called an absolute temperature scale. The classic absolute temperature scale, the one that everyone uses, is called Kelvin. Whereas Fahrenheit is an F, Celsius is a C, Kelvin is a K. So 0 K, and there's no degree sign. It's not referred to as degrees, it's degrees Kelvin, it's just Kelvin. 0 Kelvin is absolute 0. For comparison, absolute 0 in Celsius is minus 273 Celsius. It's really way down there. And minus 459 Fahrenheit degrees Fahrenheit is absolute zero too. So they're really cold. That doesn't mean that no one ever explores that territory. It's done routinely now, getting very close. You can't, in principle, you cannot get to absolute zero for reasons that will have to do with thermodynamics. We'll get there down the road. It's statistically impossible. It's not that it doesn't exist. It's just you can't. Getting there involves statistically improbable things, and you never manage to roll the dice or flip a coin heads a million times in a row. It just doesn't happen. So you don't quite get to absolute zero. Anyway, the point of all this then is if we use an absolute temperature scale, then this notion that doubling the temperature doubles the pressure, that works. And I can show you some of this. So to do this, I can't get to absolute zero, but I can get 3/4 of the way there. And the 3/4 of the way scheme that we'll use is this stuff. This is liquid nitrogen. So it's obtained from the air. And we'll learn a bit about how to make this. And I can do it in real. When I look at how an air conditioner works, they basically use, it's a very souped up version of an air conditioner that manages to make liquid nitrogen, to cause the air in the room to condense. It actually is liquid nitrogen as opposed to liquid air for an important reason. They initially make liquid air. That's the easy stuff to make, and that's what they used to use long ago to make really cold things. The problem with liquid air is it's primarily a mixture of liquid nitrogen and liquid oxygen. And liquid nitrogen boils more easily than liquid oxygen. The nitrogen evaporates more readily. And so if you have a container of liquid air sitting around for a while, the nitrogen leaves first, and you're left with liquid oxygen. And liquid oxygen is kind of hazardous because it supports combustion way too well. So there were, after some number of bad fires associated with tanks of liquid air that were allowed to gradually evolve into tanks of liquid oxygen, they now distill away the oxygen. Maybe they use it for something else. They just work with the nitrogen.
Just in case.
Oh, thanks. Okay, so this is liquid nitrogen. It's boiling away because from its perspective, this room is way too hot. So just as if you took a container of water into an oven environment pick your 350 Fahrenheit or 170 Celsius. If you have a container of water, it's going to be there boiling. This is way too hot for it to remain a liquid. So the room is way too hot for it to remain a liquid. It's in a container that makes it very hard for heat to get in there. So it's boiling relatively gently. But still, it's boiling. Incidentally, just for fun, my usual statement is that any excuse for liquid nitrogen is a good excuse. It's on tap in this department. It's just part of life. And if I pour it on the floor, or I should say, when I pour it on the floor, from its perspective, it's like pouring water on a hot griddle. So it skittles around, the little balls. And they will pick up dirt and carry it with them until they, can I pour it so it doesn't go too super fast? There's a wave of little beaties flying across the room, full of dirt now, because they pick it all up, and then when they dry up, evaporate away, they're sitting on a skin of gas created by the boiling. They're just from their perspective, they're on a hot griddle, and they're just skittling along on a layer of nitrogen that's evaporating off. So we can do that more after class if you like. The only problem with pouring too much liquid nitrogen on floor tiles is it freezes. The freeze-thaw cycle breaks the glue. And so my lab has lots of tiles that are no longer there. They froze and cracked and came up. Okay, so that's real cold stuff. It's 78 Kelvin, 77, 78 Kelvin in equilibrium here, boiling away at atmospheric pressure. You don't want to use air. I'll show you what happens with air later. I want to use helium. So this is helium. Lest you not believe that it's helium.
hello, it's really helium. I'm definitely talking with helium in my lungs, and I'm blowing it out. And the reason helium does this is because the speed of sound in helium is much faster than in air.
I gotta make sure I get it all out of me. Does not support life, right? You can breathe fine, but there's nothing there for living. Anyhow, the speed of sound is faster, and so it's lots of fun. Okay. Anyway, having done that, my father would be horrified. No, never do that. Okay, but I did it. So I'm going to fill this with helium. I guess I should find out how. That's good. Okay. And the helium is trapped in there. Don't. No. I almost lost it. Okay. So it's the helium. It's got a certain number of helium atoms inside there. They're producing the pressure necessary to keep the balloon all fat and happy. But if I chill the whole thing down, and I should say also, another observation, the rubber in the balloon tolerates incredible abuse. You'll see I'll get even worse in a minute. But it's tolerating this. So I've now reduced the volume of the balloon by about a factor of 4. How do I know that? Because I've reduced the temperature by about a factor of 4, so the density has to go up by a factor of 4 to maintain atmospheric pressure. So I've gone down in density, up in density, down in temperature, both by a factor of 4. And then if I put this out there like that, the density is too high for it to float. It's now, up and up it goes. Hey, enjoy the ceiling for a day. Okay? We'll talk about why that floats very soon. But the point was that while it was really cold, the helium had to become much denser, pack the particles about 4 times as close together on average, 1/4 the volume, in order to maintain atmospheric pressure, because each atom's not traveling very fast anymore. It's been cooled down. And at that time, incidentally, and I guess I should say that the balloon, therefore, was small, and the buoyant force on it, which is equal in amount to the weight of the displaced air, was small, because it's not displacing very much air. So the buoyant force was dinky, and the balloon weighed too much to float. But as the balloon reinflated by heating up back to normal, it occupied more space, displaced more air, had a bigger buoyant force. And eventually the buoyant force was more than its weight, and up it went. Okay with that? I promised to play with air. I put helium in there, even though I'm not really ready to talk about how helium balloons work, how helium balloons work, because of a problem that occurs with ordinary air. Let me make an air-filled balloon. So now you think when I cool this air to 1/4 its original temperature, its density is going to go up by a factor of 4 to compensate. Well, that's not quite what happens. I'm melting, who could believe my glorious wickedness, whatever it is. I can't remember the Wizard of Oz, it's been too many years. It's tiny, what happened? The air liquefied. So this is one of the reasons why I say that relationship between pressure and density and temperature, it's a good approximation, but it's not perfect. It's got some flaws. For example, it imagines that the gas stays liquid at all temperatures. The gas stays gas at all temperatures. In fact, it doesn't. It turns into a liquid below a certain temperature. And so I just liquefied the air inside the balloon. You okay with that idea? Oh, come on. So I'm going to liquefy the air inside the balloon. One of these days I'm going to get creamed by this demonstration, but I still like it anyway. 2. So I'm liquefying air in the balloon, then reinflating it, then liquefying some more air in the balloon. 3. Not enough explosions in this class. 4. Can't do this in a class on Shakespeare. You can dress up in period garb, but that's about it. I know from experience that I got to go to about 10, alas. If I go short, we're sitting there for ages watching this nasty thing get bigger and bigger and not pop. I think I'm at 6, give or take. 7? Am I 7? I'm not being very generous with the fills either. I'll do one more and then I'll tie it off. So I've liquefied a lot of air inside there. It's got way too many air molecules, I hope. All right. Thanks, Al, for doing the remote control here. Yay! Yeah. Okay. So you now see why I used helium. The reason I used helium to show you that this factor of 4 effect, go down factor of 4 temperature, you go up in density by a factor of 4, is because helium is very hard to liquefy. The molecules barely stick to each other. And to liquefy helium, you have to get down into the range of like 4 Kelvin. It's one of the coldest, liquid helium is one of the coldest substances in existence. It's used to study really cold phenomena. Okay, so just to come back to the notion of playing with temperature, you can make a hot air balloon float. I should point out, this balloon, when I fill it, which I'll do in a minute, I fill it with hot air, we don't have to seal it. The balloon has no tension in the envelope. It's not an elastic balloon. We just have to get to the point where the pressure inside and the pressure outside match. And the limp skin of the balloon will just sit there, not accelerating toward or away from the contents of the balloon. But in order to make the balloon weigh less than the buoyant force on the balloon, we need to fill it with something that's relatively light, has a relatively low density. How do we do that? Use low density air, which by itself would have too little pressure to keep the balloon inflated. But let's heat the air up so that we're compensating for the lack of density with an excess of temperature. And then you've got a system that has atmospheric pressure, but the density is small, smaller than the ambient air density. Any questions about that idea? I just want to make sure everybody's on board. What are the effects of helium-filled balloons and air-filled balloons when released in space? If there's no air around, the balloon is going to, in principle, would inflate to infinite size. So it's all a question of what's the skin of the balloon like? Can the skin of the balloon tolerate the tremendous pressure? No pressure outside and probably pressure inside. And a steel balloon could do it. These balloons couldn't do it. They'll burst. So I'm putting very hot air inside this. The pressure across any part of the wall, there's no pressure difference. So once it's inflated, so the limp skin of the balloon is perfectly comfortable. It's in equilibrium. And there's no pressure difference even at the bottom. So there's no tendency for gas to go in or out of the bottom of the balloon. And this is how most hot air balloons work. There's no seal on the bottom. It's open. So the pressure right there and the pressure here, it's atmospheric, both sides. Okay? Once it cools off, it comes back down. I think these balloons, this actual balloon, you can fill it with air and let sunlight heat the air inside up. And they float off. Probably they get into air traffic problems. They just float up there supported by sunlight. They're hot air balloons heated by sunlight. All right, but we're not doing that. Any questions about how hot air balloon works then? For practical purposes, when you go hot air ballooning, there are a number of companies that do this in Charlottesville, and it's pretty fun. I've done it twice, floating around like this. You're just a bubble in the atmosphere floating along, suspended by the buoyant force in a balloon that weighs less or approximately the same as the air it displaces. Buoyant force is basically matches. David? Why does like a bubble of air in water? A soap bubble by itself, normal soap bubble filled with air, doesn't float. It's almost neutral. It's almost weighs the same as the buoyant force on it, but the skin of soap is just a little too much. And so it still sinks. But we can put gas inside that's not air and make it weigh less so that it actually does float. Is that okay? Soap bubbles, they go with the wind because they're so nearly net force zero. They weigh a little bit, and they do come down and it's still air. But if the wind's blowing, they go off with the wind. Your breath, maybe the heat of your breath, the fact that you're blowing with hotter air than the ambient, they may actually rise briefly. I didn't even thought of that. They probably do go a little, just a little bit up. But we can put lighter than air gas inside. Other questions? Yeah. The balloons in space? If you took a balloon that can't tolerate the balloon is going to try to expand because it's going to have no air push, no pressure pushing in, definitely pressure pushing out, albeit smaller and smaller as the balloon gets larger and larger. It may hit an equilibrium it can tolerate, where the balloon has swelled to the point where the pressure inside is now so small that the skin of the balloon pulling in and the pressure of the dilute gas inside pushing out, they balance, and the balloon just sits there forever. That's possible. More likely with these balloons, if you put any reasonable amount of gas in, like more than a tiny, tiny bit, they'll eventually get, that tension will get too big and the balloon will burst. I mean, an example I'm thinking of is there are surely many space movies, but Space Odyssey, the original Space Odyssey, which is now, was made in the age of the dinosaurs, there's an episode where one of the astronauts has to go through space. And basically, we're like a balloon, because we're air-filled lungs, and in empty space, that's bad for us. We will tend to expand and burst. Or alternatively, if you breathe out, all the air will come out of our lungs completely, just bone dry. So it's not good for us to be like that. But you should be able to actually hold your breath with a few air molecules left inside, not many. Too many, they'll burst you. Is that okay? Okay, so this is hot air floating. Yeah, the hot air balloon rides, I mean, they like to do it on days that are pretty still air for obvious reasons, because you don't really want to be there in a thunderstorm. And they also work best in cold air, because when cold air is relatively dense, the air molecules aren't traveling as fast, so they pack more closely together at the usual ambient pressure. So cold air is better for hot air balloons. It's better for airplanes. They fly better in it. It's just thicker, denser stuff. The air is. The hot air balloons have a flight limit on the envelope that's related to how hot they heat the envelope. If they try to balloon around on hot days, they need to heat the air a lot. And that means the inside of the envelope gets very hot, and it gradually ages. And so they prefer to fly in cold weather when they don't have to heat their balloon that much and wear it out. Okay, what I wanted to do before I run completely out of time is, how about helium? Why do helium balloons float? Helium balloons float because it turns out that when I told you that that pressure is proportional to density and times temperature. Density isn't really the quantity that we want to be working with. Density is how much mass there is per volume. What we really care about is how many particles are there per volume. And the reason for that is, it turns out that if you substitute, if you have two balloons, this balloon and that balloon, that one's got helium in it, this one's got air in it, they contain about the same number of particles. In this case, the particles are air particles, which are pretty heavy. In that case, the particles are helium particles, which are very light. If you counted them out, effectively you count the same number in the two. So because that one has so few, it has the same number of particles, but they weigh 1/7 as much on average as these guys do. That has less weight and therefore floats in air. The buoyant force exceeds its weight and up it goes. Have I set it up? The lecture video talks more about the idea of what's called particle density. So instead of paying attention to physical density, that is how much mass there is per volume, pay attention to how many particles there are per volume. That's really the quantity that's most important in these stories. So as we change temperature and change particle density, we change pressure. So about helium balloons, helium floats because the particles, although they're very light, manage to, where'd the balloons go? Although helium is very light, do I want to do this? Nah, we need the time. Helium can fill the balloon by virtue of its particles and still get atmospheric pressure. Helium is not the only lighter than air gas, which is where I'm headed. The classic second choice lighter than air gas is hydrogen, which is dangerously flammable, the famous Hindenburg and all that stuff. The other commonly occurring gas that's lighter than air, that is, the average weight of this gas's particles is less than the average weight of the air's particles, is natural gas, as in methane. And I need somebody who likes to light bubbles on fire. Alex, thank you. So here's the idea. We're going to blow soap bubbles. This is apropos of David's question. Normally, soap bubbles won't float very well, maybe a bit. But if we fill them with helium, they certainly will. But that's boring because you can't burn helium. But you can. So let's see, this is a two-part thing. You get the torch here. I'm going to light it. And your job, along with lighting, come on, where's this? Okay, your job is not to light me on fire, okay? Light the bubbles as they go drifting by here. I'm going to blow bubbles. And as they go by, you get to light them. And they really do. You can see they're really buoyant. They love to go up. And even if they burst, you can still, the bubble is effectively still there, skinless, but so you can still light it. The full history of this is I had a friend in high school who used to send up bags filled with natural gas and a fuse. And then he would sit on the police radio and listen for UFO reports. Okay, two more and then we'll call it a day. You understand why these guys are floating? They're clearly at atmospheric pressure, but because the particles involved are so light, the buoyant force upward exceeds their weight downward. And last one. And it's off. Okay. Thanks.
Yeah, thank you.
All right, we'll see you on Monday.